Hi, ladies and gentlemen. This is Mr. Green, and this is another in my lessons in geometry. Wanted to let you know this is probably going to be the last one for the semester that I'm going to be giving you, and I'm really appreciated and enjoyed this semester. But we have reached the end of Unit 5, and so this might be the last recording you'll get from me. We might have a few more class connects, and we'll do a review of Unit 5 and of the entire semester before we take the unit test. But for right now, no more recordings. So don't forget, do the corrections. Get everything turned in by the due dates. Those are the important things about the course. You get things turned in, you get the corrections done, you will get the grades, okay? We're taking up the concept of a coordinate proof. Now, so far, all the proofs we've done have been very, very detailed in the sense that we've had one step followed by another step, and you've had to figure out the reasons behind doing different things. A coordinate proof is a little bit different. We're going to use the formulas that we have had, the formulas that we have been given in this course to try to figure out how to do things. So if I were to take a point K, let's see, we can use a coordinate proof to show that for any point, its reflection across the xy, across y is equal to x, then y equals x is a perpendicular bisector of the segment connecting the points and its image. So how would we go about doing that? Well, if we're wanting something perpendicular and we want to show that it's a perpendicular bisector of something, one of the ways that we might be able to do that, it says right here perpendicular, is by using slope. So considering I've got 2 points, I could find the slope of the 2 points and compare them. If their slopes were negative reciprocals or their product was -1, then we would say that we have perpendicular lines. If we're wanting to show that they are bisectors of each other, we could use the distance formula and find the distance from the 2 points, and that would tell us whether they were being bisected, divided in half. So that's what we're doing in a coordinate proof. We're using the formulas that we've been given to prove things that we know about a particular object. Back up here a second. One of the important aspects of doing coordinate proofs is being able to put objects where it makes sense. Okay? So if I were wanting to do something with this type of an object, I might want to think about placing that object right at the origin. Why? Because a lot of my calculations involve using 2 points. And if I can use the origin as one of those 2 points, that means I've got 0, 0 in my calculation. And if I'm subtracting 0, I can do that in my head, and I don't have to use the calculator for it. Or if I'm adding 0, I can do that in my head, and I don't have to use the calculator for it. It really helps if we can use this origin, this 0, 0 point, to help us, because it will simplify our calculations. For example, if I were looking at this triangle, depending upon what I was wanting to do, I might try to put the right triangle right on the origin. That way I could very simply use that 0, 0 point to calculate things. I might want to draw that triangle so that one of the other vertexes was there. It depends upon what I was trying to calculate. Okay? It becomes a question of placement and where is it most easiest to do the calculations. So you have to think about these things. If I'm looking at a trapezoid, even though it seems like it'd be easier to put it at the origin, a lot of times what we have found is that if we straddle the origin sometimes, it helps us. Okay? By straddling the origin, we get that equal numbers on one side and the other side, and they kind of offset each other, making it easier to do the calculations. So 3 and -3 give me a 0, okay? And a -5 and a +5 give me a 0. So it makes it easier for us to do some calculations that way, okay? That's the whole purpose of placing figures where we want to place them. So Here's our first question. It says, show that the midpoints of a quadrilateral form a parallelogram. Okay, midpoints. That means I need to use the midpoint formula. Okay? So what I would do is I would write down that midpoint formula, which is what? It's x plus 1, or x plus x, x1 plus x2, divided by 2, comma, y1 plus y2, divided by 2. And that would be my midpoint. What am I going to do? I'm going to find the midpoint on each one of the four sides of this thing here. And once I find each one of those midpoints, I will have something that I can work with. Okay? What do I do with those points once I have found them? Well, you know what? Locating them means I probably need to identify them as values so that I can refer to them. Okay? So once I find A and B, I can find slope from A to B. I can find slope from, that is AB, sorry, from A to D. I can find slope from B to C, and slope from C to D. Once I find these four slopes, you know what I'll discover? I'll discover that AB and CD are equal, and AD and BC are equal. Once I've got equal slopes, I know I've got a parallelogram. So I just showed you how I would go about planning and doing a coordinate proof. I would say in step 1, given these points, and I would list all four of the points. Step 2, here's the midpoint between the first two. Use the midpoint formula, find it. Reason for it, midpoint formula. Step 3, find the midpoint of the next one. Reason, midpoint formula. I would find each of the four midpoints. So I'm up to step 6 because I've done 5 steps at this point. I would then say the slope of the midpoints from A to B would be this, and I would find the slope of it using the slope formula. Finding each one of those, 9 steps. At the end, 10. Equal slopes means parallel lines. Since AB and CD are the same, these two lines are parallel. Since the other two sides are also parallel, therefore it must be a parallelogram. Is this the only way of doing it? Nope, I just use the midpoint formula and slope to get here. Are there other ways of doing this? Why, sure there are. You could find where these midpoints are. You're not going to be able to get by without not doing that. But you could then say, you know what? We could connect the diagonals here. And we can find out if the diagonals bisect each other. Why would the diagonals bisect each other help? Well, that's one of the things that we can say is true about a parallelogram. The diagonals bisect each other. Do you see what I'm doing? I'm using the thoughts that we did in Unit 4. I'm using the formulas that we had. I'm coming up with a proof based upon all those formulas. And I'm just saying what formula I'm using every single time. It can be complicated, but it can be much easier than trying to prove it with geometric information. Okay? So, I appreciate you guys sending me the fact that you were in geometry first semester. It helps every time because it does mean I can find your information and answer your questions really quickly. And I do like to get your answers to you as quickly as I can. Okay. Well, I will see you in Class Connects, and I've enjoyed the semester.